Sometimes when you look at a chemical formula, it can be difficult to tell what the charge on the metal ion should be. Now, if you have a representative metal, like barium here, it's pretty easy, because barium is in group 2A on the periodic table, so it always has a 2+ charge when it ionizes. However, if you've got a transition metal, like say lead or manganese, it's a lot harder, because they have multiple possible oxidation states. So we have to use a trick to figure out what the charge is on the particular metal ion in this compound. Now, I'm going to start out showing you on barium, which we already know, as I said before, is 2+, but we're using it for our first example so you can see the logic of what we're talking about. So, when we look at any ionic compound, remember, the total positive charge has to equal the total negative charge, and those two combined need to give us 0. If we imagine that we didn't know that barium is 2+, we can figure out what the charge should be by looking at the charge on the anion, the chloride. Now, chlorine is in group 7A, so when chlorine ionizes, we get chloride, Cl-1. And we have 2 of them, as you can see right here. So, if we have 2 chlorines, the total negative charge is 2-. Now, like I said before, the total charge on the whole compound has to be 0. So the question is, what is the charge on the barium that would cancel out or balance out our 2-? And of course the answer is 2+. In this case, the barium ion has a 2+ charge to it, because 2+ and 2- together give us 0. Now, like I said, with representative metals this is kind of silly because we can tell by looking at the periodic table. However, with transition metals we need to use this trick to determine what the charge state is. So down below, let's look at lead oxide with the oxygen here. A single oxygen is in group 6A, so oxygen, when it ionizes, has a charge of 2-. And there are 2 oxygens, so we have 2 total O2- involved here. And the total negative charge from that is 4-. Now, that 4- has to be canceled out by the charge on our lead. There's only 1 lead there. Remember, we don't write 1, so if it's blank it means 1. There's 1 lead, so all of the total positive charge that'll cancel out our 4 has to come from the lead. If the total negative charge is 4-, the total positive charge has to also be 4+. So this is lead 4 in this particular case, lead with a 4+ charge. I'm going to do a few more examples, see how this works. Moving down, we're going to find the charge on our manganese by looking at the chlorine. Now, I'm not going to draw all of them because, as you can see, there are 7 of them right here. So instead, let's use a little bit of math. We have 7 times our chloride ion gives us a total negative charge of -7. We look at the total number of manganese. Remember, there's an invisible 1 right there, because whenever it's blank it means 1. So if the total negative charge is 7, the total positive charge has to match it, has to also be 7, which means in this case, manganese has a 7+ charge, the manganese 7 ion. You'll never get a number that big with representative metals, but it can happen with transition metals. If we look at some others down here, we'll do these 3. This same logic holds even when you have something more complicated, like a polyatomic ion, a phosphate. We work it the exact same way. So if we want to know what the charge is on chromium, we just look at the phosphate. Each phosphate, PO4 3-, has a 3- charge. There are 2 of them, so 2 times 3- gives us a total negative charge of -6, or 6-. Now, before, in our previous examples, there was only 1 of what we were looking for. Now, however, there are 3 chromiums. So that +6 that we're going to have is divided up among the 3 chromiums. So each single Cr has a 2+ charge. It's only together that they get that 6 plus. Same way, sulfate, SO4 2 minus, and there are 3 of them. So 3 times 2 minus is still minus 6. To find the charge on the aluminum, there are 2 aluminums, so our plus 6 has to go into 2 separate atoms. Each aluminum is 3 plus. 2 times 3 plus is plus 6. Last one for right now, we can look at the tin, find the charge on our SN, our tin here, by looking at the charge on phosphide. Remember, IDE means it's a single element. We have phosphide here. Each phosphorus is 3 minus, and there are 4 of them. So 4 times 3 equals a total negative charge of negative 12, our biggest one yet. Divide it up, divide our positive 12 by our 3 tins there. 12 divided by 3 is 4. Each tin in this case has a 4 plus charge.